How can you tell if your incoming second graders have meaningfully learned to write equations? Well, when they see an equation, can they tell a story that matches that equation? When they hear a story, can they write an equation that matches the story? The types of equations that I'm discussing in these two questions are called situation equations. Chances are that your incoming second graders can meaningfully write equations for some of the easier problem types, but may still struggle with turning words into equations for the more difficult problem types. Common Core Standard 1 under the Operations and Algebraic Thinking strand particularly mentions the need for students to be able to formulate such equations to match specific problems. Mathematical Standard of Practice 4 is Model with Mathematics. This looks different at different ages, but the Common Core authors specifically make a connection between modeling with mathematics and writing situation equations, as you can see here. In order for children to meet this standard of practice, they will need more than an assignment that just asks them to write situation equations. Equations will need to be meaningful representations for them, and this includes being able to explain how the equation and the situation are related for a whole host of problem types, and recognition that the equal sign demonstrates an equivalence. Clearly, second graders don't just develop this level of expertise on their own. As we've discussed in previous lessons, they often have trouble identifying which operation is embedded in the word problem, let alone being able to write an accurate number sentence. In this lesson, we're going to examine some important mathematical ideas and instructional strategies for supporting learners in developing this skill set. Solving word problems essentially involves three steps: converting the words to arithmetic, which would be where we write an equation, then solving the arithmetic problem, and then interpreting the solution to obtain an answer to the original problem. The third one, often students forget to do this. It's not necessarily cognitively difficult, but oftentimes they forget to do it. The cognitive difficulty in solving word problems is on step 1, pulling out the meaning of the words and converting that meaning into the symbolic language of math, writing the equation. It's at that point, number 1, where our proficient learners are able to just move forward independently, and our basic learners turn to us with an appeal for help. What is this, an add or a subtract problem? So how do we scaffold that step to make it more achievable to a broader group of our learners and support them in building the independence they'll need for future learning and also for standardized testing? The Common Core authors suggest the use of diagrams as a useful tool to support learners in seeing these mathematical relationships that are embedded in the problem. Diagrams serve as a useful tool for making that relationship clear. Oh, I see it now. It becomes easier to see what you have to do next. Furthermore, since it makes the number relationships clear, it also makes the equation more obvious. As children relate words to diagrams, diagrams to equations, and the equations back to the words, they're able to develop meaningful understandings of equations as mathematical representations. Diagrams are useful, incredibly useful tools for helping learners to make sense of and visualize those mathematical relationships embedded in words, and as a result of that whole sense-making process, they also gain a deeper understanding of operations and how operations are connected to one another and how the operations are connected to the equations. In some cases, such as the one you see at the bottom of the slide, a situation equation is not really easy to solve in its current form. So blank minus 15 equals 5, that essentially means I have a start unknown. I have a certain quantity of something, and 15 of them are removed, and now I have 5 left. If students can come up with that situation equation, it's still a little bulky to solve. We could use algebra and convert it to the much easier 15 plus 5 equals blank. But we don't have algebra in second grade, at least not formal algebra. Visual tools can make it clear that these two equations are connected and basically are saying the same thing. They can make that clear in a way that the symbols can't. We're going to revisit that idea soon. When children first start problem solving, it's not uncommon for them to draw pictures to support their sense making. That's an important stage in their development. But when they get to second grade, many of those early representations are just inadequate for the size of numbers that they're going to be working with. Also, the drawings that children do in their early math work tend to be idiosyncratic. They're suited to just that particular problem. By second grade, we need to foster more efficient use of diagrams. Diagrams as heuristics that can be applied to a broad range of problem types. The Common Core authors suggest the tape diagram as one such useful tool. As you can see here, it's a very versatile tool. It's capable of being used with all of the addition and subtraction problem types. It can also be adapted for work with multiplication, division, fractions, percents, and ratios as children progress through the elementary curriculum. In these diagrams, you can see that the model works somewhat similarly for most problem types, although the way you conceptualize what each part stands for is a little different. The bars can also be drawn different lengths, allowing you to build the idea of magnitude. So if I were modeling a problem that had two addends, 5 and 15, I would draw one of the bars much smaller than the other. Compare problems, which you see in the bottom right corner, work a little bit differently. Here we separate those two bars and align them on the left side so that we can see the part that sticks out. That's the how many more part, or the extra part, or the difference. So we usually draw them as two separated bars. As is the case, though, with all worthwhile mathematical tools, it will take teacher modeling before these tools are used comfortably by students. And the teacher also needs to intentionally model how to write equations, not just tell how to write equations, model the writing of equations. And to do so, it helps if the teacher has some background knowledge. If you understand generalizations about how equations function, then it helps you in terms of what you say while you're modeling and also what kinds of questions you ask while you're modeling. I actually don't recommend that you give a lecture on how to write equations using this slide as background. This is teacher information. If you try to lecture it in that way with students, you're likely to confuse them. The ideas that are embedded in this slide make most sense when they're embedded in a real context, so while you're working with real problems. Over time, with modeling and dialogue, students can perceive these generalities, and then you can formalize them on a chart. The length of time that it takes to model, of course, will depend on the background knowledge of your class. On this slide, I've illustrated 3 types of generalized situation equations. On the left, we see the action problems are characterized by a starting amount, a change quantity, which is also associated with either an add to or a take from action, so that will indicate whether you use a plus sign or a minus sign. And then after that change, you have a new resulting quantity. So you have 3 quantities and also a type of action. And that can easily be used to formulate a situation equation as shown here. This should be fairly simple for most second graders. When the problem is a result unknown, chances are they already came in knowing how to do this for a result unknown problem. But some of the more difficult problem types like start unknowns, they're probably going to struggle with that. At the top left-hand column, we have the class of problems called put together take apart in the Common Core. They're essentially part-whole problems. And the key here is to analyze the problem using this idea of parts and wholes. Once you know, oh, this is a part and this is part and that's the whole, you can construct these equations. Part plus part equals a whole, or a whole minus one of the parts equals a missing part. And then in the bottom left-hand corner, we have the compare problems. They're particularly difficult for many children, and it helps if they're able to think of the problem as taking the larger quantity and breaking it into 2 parts. Now I can conceptualize it as a part-whole problem when I do that. So if I take the larger quantity, I'm going to break it into 2 parts. One part is the same as the small quantity, and one part is the extra, or the how many more. This extra can then be named as, we're going to call that the difference, because that isn't actually obvious to most learners. So once, it's probably going to have to be made explicit. And then once you make that conceptualization, we just go back and think of it similarly to those part-whole problems, as I mentioned. Now, the understandings that I'm talking about here, it represents some serious second grade mathematics. To meaningfully understand these concepts requires students to have some prerequisite knowledge about the nature of addition and subtraction and the relationship between the operations. Initially, when children start to problem solve, they may end up choosing an operation based on their perception. For example, if the action in the problem is add to, perhaps they will add. although this will cause problems if they do that when there's an add to change unknown problem or when there's a start unknown problem. Also, it causes problems, the perceptual tendency does, when they are approaching compare problems that have misleading language. And those difficult problems are all marked for mastery in second grade. So in second grade, we're really going to be pushing them to move beyond a perception of what an operation is. It feels like a subtraction problem. We need them to get past that and to be able to see what it is mathematically. So we need the children to understand that addition problems may not have any additive action or any clue words. These are not the things that make addition addition. Rather, addition is characterized by a situation where you know two parts and you're trying to find a whole. And subtraction is characterized by a situation where you have a whole and you know one of the parts, but the other part is missing. If you can conceptualize that, then mathematically you know what addition and subtraction is. We also need students to understand how addition and subtraction are related, and this involves so much more than just being able to write out fact families, which some children tend to do in a rote fashion. We really need them to understand the relationships well enough to leverage that information during problem solving. The number bonds you see here show the generalized relationship that addition means knowing two parts and trying to find a whole, and subtraction means knowing a whole and one part and missing the other one. I have these posted right now with a group of second graders that I'm working with, and we're moving into this idea of how to turn that into equations as well, which you've seen here. So the number bonds with those accompanying generalized equations can be used to help the students see a relationship. If the students think about what a number bond looks like as they read a problem, they're going to be able to more accurately determine what operation to use. Also, children will need some concrete experiences to help them make sense of the commutative property. And when students understand what makes something addition or subtraction, then that's a good time to introduce these more generalized generic equations that they can think of. The generalized equations are very useful in one regard, and that is in helping them see where the whole is. In addition problems, the whole is alone on one side. It doesn't have to be on the right side. It could easily be on the left, but it is alone. And in subtraction, the whole is always to the left of the minus sign. Again, it doesn't have to be the first thing you see. That rule could get them into trouble, but it is always to the left of the minus sign. One way to get students thinking about the relationship between addition and subtraction is to show them a number bond and have them write as many accurate equations as they can using the information. Their equations should incorporate an unknown, as this is specifically stated in Standard 1 under the second grade Operations in Algebraic Thinking. You can suggest that some of their number sentences need to be addition and some need to be subtraction, and they should also be able to use the number bond to justify why those equations are accurate. This type of exercise will be most successful, however, if you model it first using a different number bond. Now we're going to take a look at how to use the diagrams and our knowledge of equations and how that can be applied to hard second grade problems. The problem you see here is considered difficult because the language of shorter would tend to imply subtraction, but actually it's solved with addition. Notice how our use of models as we work through this will make that obvious to children. We're going to approach this with 4 steps. First, make sense of the problem. Then represent with a diagram before writing the equation and then solving. When I ask them to make sense of a problem, we typically read the problem first, and I might read it myself and then have them read it with me a second time. Sometimes I cover the numbers up when I want them to focus on the language. In this case, I've covered the numbers because I want them to focus on the second sentence to figure out which boy is taller without even seeing the numbers. I might have them turn and talk to one another so everyone gets a chance to justify their thinking and or critique the reasoning of others, as suggested by Mathematical Standard of Practice 3. By the time the dialogue finishes then, I expect learners to be able to tell me which boy is taller and to help me decide which boy goes with which of these 2 bars that I'm going to use to represent their height. And now I reveal the numbers and ask them to help me think about where these numbers could be placed on our diagram. We complete the diagram by referring often back to the word problem. One thing that we definitely want to stress is to make sure that our diagram shows the unknown. The diagram is going to be our main tool for determining the equation, so we need to be able to see where that unknown is. Now, take a look at the diagram. Do you see how the diagram reveals that our unknown is an addition problem? To find the unknown, we essentially have Joshua's height plus 29 more. That's not very obvious in the words, but the diagram makes it obvious. From experience, however, with this compare problem, I'm just going to give you a little hint. I can tell you that the hardest part of these compare problem models for children is often getting comfortable with labeling the difference. So that's going to take some explicit modeling, helping them see that the part of the bar that hangs off the edge, so to speak, that protrudes outwards, that's the extra, that's the difference. So that's going to require some careful modeling. Although you wouldn't have to use a number bond in addition to a tape diagram for a problem, if you're really working with students on trying to see addition as two parts with an unknown whole makes an addition problem, then you might want to choose to show a number bond here to illustrate that point. Now at this point, the class is ready to generate an equation and justify why it makes sense for the model. And so we would go ahead and use the model to construct 135 plus 29 equals our unknown, which could be a square, a question mark, an x. So at this point, they're ready to solve, and I usually have them make a decision about whether this is a good number combination for practicing their mental math or whether they think these numbers are better suited to the standard algorithm. Different children may choose different options. Now, let's take a look at a two-step problem. Jimmy is 96 centimeters tall. He's 12 centimeters taller than Evie. Find the total height of the two children. As children draw out the tape diagram after they've made sense and figured out that Jimmy is the taller of the two, when they draw this out, it's going to become obvious to them that they can't solve the problem until Evie's height is found. So you can then elicit from children a plan. Oh, so first we have to find Evie's height, then find the total height. 2 steps. And in this way, you're supporting them in an important problem-solving behavior to plan a strategy. We can then use the tape diagram to figure out an equation for Evie's height. She's 12 centimeters less than Jimmy's 96 centimeters, so that's 96 minus 12. Once we have solved for her height, we can then re-examine the tape diagram and construct a new equation for the total height. Another important part of problem solving is to recognize what the answer means in light of the original problem. So I usually require a complete sentence answer for word problems. Notice that this two-step problem was represented with one diagram. Sometimes children find it easier to model a problem in 2 steps, and sometimes it is just awkward to put everything into one diagram. So we're going to take a look at one more example, and in this example you'll see that 2 diagrams were used. So in a game, Lauren and Rosa scored a total of 128 points. Lauren scored 81 points. Who scored more points? How many more points? I might introduce this problem with some prompts. So this problem's about Lauren and Rosa. What are they doing? Oh, playing a game. Do we know who's winning? No? Is that what we're trying to find out then? Do we know how much Lauren scored? Do we know how much Rosa scored? No. Well, can we find out who's winning without even knowing how much Rosa scored? Turn and talk to your partner about what you would do first to tackle this problem. Although you don't see it on this slide, after eliciting this information from children, I like to put a strategy on the board. 1, find Rosa's score. 2, find how many more. I do this to help the learners keep track of where we are in the problem, because some students might find Rosa's score and then just think they found the answer and stop. And I'm also trying to model strong problem-solving behaviors that I want my students to gradually adopt as their own. There are some very prevalent misconceptions about the equal sign, namely that the equal sign is a signal to compute or a signal that the answer comes next. This misconception essentially means that they don't understand what equations really mean. As we model equations, we really need to be careful about how we're using the equal sign, because an equation is essentially a representation of equivalence. It doesn't mean the answer is coming next. But children often miss that message. And often we as teachers tend to treat this equal sign ourselves as if it were a signal to compute or a signal that the answer is about to come next. Notice the example shown here of 57 plus 28 off to the right. The first example shown, a student might do that or a teacher might do that modeling on the board, but that would be an inaccurate representation because the equal sign is being used to say what comes next. But notice if you look at it, 57 plus 20 does not equal 97 plus 3. It isn't an equivalence. So that would be an inaccurate use of the equal sign. You might consider introducing an arrow as a symbol for gets me to, because a lot of times students, especially doing mental math, they need some kind of a symbol when they're recording their mental math strategy, and the equal sign isn't always the most useful there unless they're willing to separate everything into multiple steps. There are some really interesting and disturbing research findings about how damaging this misconception can be, that equals means get me to, or the answer, compute now, the answer comes next. So we really want to try to get past that. We want children to see that the equal sign is an indicator of equivalence. We might do that by making sure that our own modeling is good, also making sure that we interchange the spoken word equals for is the same as. And we also want to show children more variety of equations so they don't end up with really limited understanding of how an equal sign can be used. So there's some exercises that we can use to help students appreciate the role of the equal sign in equations. And we're going to take a look at these next. These are true-false equations. You present them to students and have them decide if they are true or false. You can present the equations to your learners one at a time, asking them if they're true or false, and then, more importantly, to justify their perspective. I encourage you to try this with your class. The results can be quite enlightening. For example, you may find some students object when you write the second equation, 20 equals 15 plus 5, because they think you can't write it that way. No, you have to write it 15 plus 5 equals 20. You can't write 20 equals 15 plus 5. If they have this objection, it's a really good indication that their understanding of the equal sign is flawed. However, you can use this exercise to engage your students in peer dialogues that are rich with justification and critiquing others' reasoning. So it's a brilliant way to use the mathematical standard of practice 3. You can also try open number sentences, which essentially work like the true-false equations, except one of the add-ins has been removed, and students are challenged to figure out what number goes in the box to make the equation true. The equation you see in blue was used in a research study, which illustrated how widespread these misconceptions are about the equal sign. The resource for that is in the references. Children with misconceptions about the equal sign tended to answer 12 or 17. I encourage you to try this with your students and see to what extent they also exhibit a limited perception of the equal sign that is not based on equivalence. These open number sentences and true-false equations are wonderful tools for sparking lively debates among your students that will help you see how they're thinking and reasoning, and which can be used to bring everyone to a more robust understanding of the equal sign. The time and effort that it takes to support learners in skillfully formulating equations that match situations is definitely worth it. Not only will it be helpful to them when they get to algebra, but it's also a highly useful tool for multi-step problems because it helps us document our thinking along the way in short, abbreviated steps, and that helps reduce the cognitive load that's required to handle all those intermediary steps in multi-step problems. We don't want children to merely learn to write equations. We want them to make meaning out of the equations as well. Since converting word problems to equations is the most difficult step of problem solving, I've suggested that we consider using diagrams as an intermediate step to scaffold the writing of equations and make those mathematical relationships clearer. A critical feature of writing equations is the equal sign, and that often gets little attention in the curriculum. We need to model the appropriate use of the equal sign and also to elicit our learners' misconceptions